Welcome AP Physics, Electricity, and Magnetism students. Today's review topic is inductors. As you can see, this is the second video of the topic, the unit induction, and it's dealing specifically with these little circuit components called inductors. So what we're going to do in the video today, we're going to first look at the concept of what an inductor is, how it works. Then we're going to learn a mathematical definition for inductance, as also we will learn the expression for the EMF or the voltage produced by an inductor. And then we're going to learn how inductors behave in inductor resistor circuits. We're going to learn an expression for the energy in an inductor. We're going to learn how inductors behave in more complicated circuits. And then we're going to look at circuits involving just an inductor and a capacitor. So there are the topics for today. But before I begin with these topics, I just want to look back at the main idea from the last review video. So you don't have to write this down because this is already in your notes. So remember that the main idea in this unit is Faraday's law. And it tells us how voltage is created through magnetic field. Magnetic field creates a flux, B times the area going through a particular wire loop, as in this picture. And then, whenever the magnetic field or flux changes, it creates voltage. Voltage, of course, drives current. So this is the way electricity is generated at power plants. But you could change either the magnetic field, the area, or the angle between the two. So that's the idea, and that's going to then help us understand how these little devices, inductors, work. So let's move on to today's topic, inductors. Okay, so first of all, the symbol for inductors is capital L, and it's measured in henries. So the concept of an inductor is any wire loop, could be any wire loop. So I have here just a simple wire loop like this, and the current's coming up like this and around in the clockwise direction, and then it continues on upward. Let's suppose, for whatever reason, oh, and by the way, that creates a magnetic field into the paper. I could figure that out by this right-hand rule, not that one. So down here, the current is going to the left, so I put my thumb in the direction of the current, and I see my fingers will poke through the loop inward. So there's the magnetic field caused by the current. Then let's suppose I attempt to increase the current. How could I do that? Well, there's a power supply feeding this current through this loop, so I turn the dial and add more volts, therefore increasing the current. What that'll do is it'll make the magnetic field increase also. We could figure that out from the Biot-Savart law or just from the concept more current, more magnetic field. So what we saw in last review video, if you have an increasing magnetic field, that's changing the flux, increasing the flux going into the page. So Faraday's law and Lenz's law says that there will be a voltage induced that will oppose that increase in the magnetic field, so the B induced will go the opposite way of into the paper, out of the paper. And then again, by this right-hand rule, we could put our forefingers up out of the wire loop, indicating the magnetic field induced, and we see that the current induced, the voltage induced, is going counterclockwise. So from induction, we can see that the voltage of this induced is opposing the current. So this inductor L opposes the increase in the current. So the I, when I turn this up with a power supply, I turn the voltage up, the current's going to lag because the voltage induced will make the current increase gradually. And I put slowly in quotation marks because what I'm saying is that the current's not going to jump up instantaneously. However, slowly, like everything in physics and science, it's all relative. It could make it increase just a millionth of a second lag compared to if there were no inductance. So slower than if this effect was not present. But it can, on our time scale, a human time scale, it usually is quite rapid. like milliseconds. Nevertheless, it makes the current gradually increase. Now let's suppose that I get the current going, and then what I do is I try and decrease the current. How do I do that? Well, the power supply running this circuit, I could turn the dial down and decrease the voltage, and that'll make the current drop. That'll also make this magnetic field decrease. Now, from what we learned in the last review video, Faraday's law, Lenz's law says that there will be a voltage induced because the flux, the magnetic flux, is changing in that wire loop. And the voltage will create a magnetic field induced that opposes that change. We're losing this, so B induced will try and keep it going, opposing the change. So which way is the voltage now induced? Well, we use this right-hand rule again. We put our forefingers down through the center of the loop, and we see that our thumb at the bottom goes like this in the clockwise direction. Now you see, instead of the voltage induced going against the current, it's going with the current. So when I is decreasing, the voltage is trying to keep it going. So the inductor now opposes the decrease instead of opposing the increase of I. So I decreases gradually or slowly. When I turn that dial down, the inductance keeps the current going a little bit longer. And then it eventually does drop to zero, but it lags for a little bit. So notice that the inductor opposes. What does it oppose? It opposes an increase or it opposes a decrease in the current. So the inductor is opposing any change in I. It's trying to keep the current steady. Okay. Now sometimes people they use an analogy in mechanics. When something has mass, it's basically going to oppose acceleration. So a large mass, it fights you when you're trying to speed it up, and it fights you when you're trying to slow it down. So mass opposes any change. It doesn't oppose velocity. Once you get mass moving, it'll keep going forever. But it opposes any change in velocity in mechanics. So very often people use the concept of mass to understand inductance. It's like inertia, keeping this current going at the same rate. So when you try and increase, it opposes you. When you try and decrease, it opposes you. It's like mass inertia, keeping the current constant. So that's what an inductance does. It's an inductor does. And it's all through Faraday's law and induction. So now we're going to move on to actually calculating the numerical value of the inductance. So here, the definition, first of all, I want to point out that in a diagram, inductors are drawn as spirals because, you can have multiple coils, and so that increases the inductance. So they are literally little coils of wire. So that's how you draw them in a diagram. Remember, a resistor is like a zigzag. A spiral, or whatever you call this, a helix, is an inductor. Symbol L, capital L, measured in Henry. So here's the basic definition. N, flux magnetic over current. Now, when we were studying flux in the last video, I used this symbol. So I just want to point out that sometimes they put these little lines here. Just be prepared. Don't be confused that these are the same things. Oh, flux magnetic B. Okay, so these are the same variable. So I switched it up just to make sure you're comfortable with both variables. So what is it? N is the total number of coils in like maybe a solenoid. And this is the flux through one coil. So this top is like the total magnetic flux of all the coils combined divided by the current. That'll tell you the inductance, the kind of inertia that something has, the circuit and the current inertia in a circuit. And then this expression is basically Faraday's law reworked for inductors, but it says that the inductor generates a voltage opposing any change in current. And the bigger the inductance, the more voltage, and the more rapidly you try to change the current, the bigger the voltage. So the voltage produced depend on both things. So there's the definition. Now what we're going to do is I'm going to do a calculation example. So what I have is a solenoid with a radius of 2 centimeters or 0.02 meters and a length of 0.2 meters or 20 centimeters and with 1,000 turns. So I drew a few turns on my solenoid, but in our real solenoid, the wire wraps around 1,000 times. So we're going to determine the inductance and the voltage in the inductor at 2 seconds if the current is given by this expression. So notice the current is some kind of parabolic function. It's going to start at 10 amps and go like this if we were to plot it, but not necessary. All right, so first thing, to find the inductance, remember that I got to find the flux in one coil, multiply by N and divide by the current. So I'm going to find the flux in one coil from the basic definition in the last review video we went over. Flux magnetic is BA cos theta. So the magnetic field is the magnetic field in a solenoid. If you don't remember that, you would have to derive it quickly from Ampere's law. This is mu zero, the constant. This is N, the concentration of the turns. Numerically, it'd be 1,000 turns per 0.2 meters. So we divide those. It's like a turn concentration, like a density of the wire coils. And then I is obviously the current in the coils. And then the area is like the area through which the magnetic field passes through, which is the area of the end of the solenoid, which is pi r squared because it's a circle. Okay, so then I just basically also replace this lowercase n. That's the only thing going on in this step. I replaced the lowercase n with what I said. The capital N, 1,000 turns per 0.2 meters, gives me that ratio, the concentration of coils per meter. So now I have the flux through just one coil of the solenoid. So now I have to take the total flux, which will be the 1,000 turns times the flux in one coil divided by the current. So that's what I do here. Notice this flux expression is in the brackets here, and N over I. And I'm working in variables because I'll plug in the numbers later. All right, so then moving on. All I'm doing is just canceling the current out here, and there's the expression for the inductance. It depends on how many wire turns you have. That kind of makes sense. More wire wraps, more inductance. The bigger the diameter or radius of the solenoid here, the bigger the inductance. And then also the length, the longer it is, the smaller the inductance. Also, sometimes they replace capital N with, if capital N is if lowercase n is capital N over L, then capital N is N times L squared. And if you plug that in, then you get this expression. But these are all just details. As you can see, I've highlighted these two steps. This is what I want you to focus on. Okay? The details you can work out yourself on the AP if it comes up. The next step, what I'm doing is I'm just plugging in mu zero here, the pi, the N, the radius that was given 0.02 meters and the length, which is 0.2 meters, and I get 7.9 times 10 to the minus third Henry, or as I write it here, 7.9 millihenries. Okay, so that's the inductance. Now for part B, what's the voltage induced? Well, I use that expression which is on the previous page, that the voltage is negative L di dt. So then I plug in the current here. I take the derivative of what's in the brackets here. The derivative of 10 is 0. So there's a 0 here that I didn't write. But then the derivative of this is negative 2. And the derivative of this is 10t, which is over here. And then what I do is just plug in all my numbers, and I get negative 0.14 volts. That's what the volts of this particular solenoid, that's what it's doing to oppose. At this moment, the current would actually be decreasing. And so it's decreasing. Well, whatever, it's the opposite direction. All right, so again, study this step, okay? Notice the B and the area. This is basically the important thing for calculate along the way. And then this step, study how this came about in the derivation. Like I said, if you can get here, the rest of the little details, you can plug those in on the AP if you want, and you'll do fine. And then this is the step I want you to emphasize. Notice I'm taking the derivative of the current multiplying by the negative inductance. Okay, so next thing we're going to look at is inductors in LR circuits. That means there's an inductor and a resistor. In the first case, what I'm looking at is I am looking at the case where the current's going to be increasing. I've got this circuit here with a switch open, so there's no current. I flip the switch down and I turn the current on, and the current's basically going to be going this way. And as we said, the inductor is going to oppose that increasing current, so it's going to push backwards on the current, and that's going to make the current gradually increase instead of instantaneously increase up to M over R. Okay? So we've got to come up with an equation for the current as a function of time. So what we have to do in that case is we've got to make a differential equation and solve it. I just want to recall, before we even begin with the details, the 4 basic steps to solving a differential equation problem in physics. Okay? So the first thing you have to do, whether it's mechanics or current, RC circuits, LR circuits, as we're doing today, is you have to make a differential equation. In mechanics, we use Newton's second law, A equals F net over M. When it comes to these circuit problems like RC circuits a couple units ago, or LR circuits like today, we use Kirchhoff's loop rule to make our differential equation. The second step is you separate the variables. What that means is you put all the current terms on one side of the equation and all the time terms on the other side of the equation. Then what you do is you integrate both sides. And then the fourth step, you plug in your limits and solve. I say this to mechanics students, I say this to E&M students. These you should remember, these 4 steps. Plug them into your mind. There's a lot of details coming. Many variables, many steps. But if you can remember these 4 steps, they're like your signposts, your guideposts to take you to the solution. Okay, so let's see these 4 steps in action. Okay, so as I said, step 1 is you use the loop rule to make a differential equation. Remember the loop rule, what I said is imagine that you're a little ant and you're going around the circuit with a little tiny voltmeter and measuring voltages. If you go completely around any loop in any circuit and you add up all the voltages, you get 0. Okay? So the little ant comes here and walks from the negative terminal of the battery to the positive. So it goes plus M. Then it goes through the resistor in the direction of the current. So this is like a river going down a mountain, the current. So you're going from high volts to low volts. That's why we do minus the voltage IR. V equals IR from Ohm's law. And then we go through the inductor, and the voltage there is negative L di dt, the expression that we had earlier in these notes. So there's step 1. I've highlighted it. That's how you make a differential equation. This is important. A lot of times, more than half credit in a differential equation problem is just making the differential equation. So, like I said in a lot of review videos, you only need 2/3 of the test approximately to get a 5 out of 5. That means you don't have to master everything. So, definitely be able to do at least this. Okay, it's totally doable. A lot of heavy stuff coming, but they're usually generous and they give you a good portion of credit right there just making the differential equation. So remember, we made a differential equation. The next thing we have to do is separate the variables. We got to get all the I terms on one side. So I'm going to slip this over here, and that leaves just M minus IR. Then what I'm going to do is divide by this entire thing. I always said that you don't add or subtract when you're separating variables. Once you have the di dt on one side, you've got to divide or multiply. So I divide this all the way down here, and then I move the L over to this side. Now when I divided this, I just have 1 on this side. So then I divide both sides by L. That gives me 1 over L. And then I move the dt over here. So I've separated the variables. Now I integrate both sides. So this is step 2 and 3, the variables separated. I integrate from current 0 to some later current, and I integrate. My experiment started at time 0 and it goes to some final time. Okay, so now this is like a natural log because I have d, I, and I in the bottom, but because of the fact that I have minus IR here, if you use a U substitution, you would see that that would generate a minus 1 over R over here, and the natural log of this entire denominator from limit 0 to I. This side, easiest integral possible, dt integrates to t from our limits 0 to t final. And then the final step, you plug in your limits and you solve for the current. That's what we're after. So notice I plug in, oh, and by the way, I moved the minus r to the other side. So then I plug in I, capital I right here. That's what I'm solving for, right? That's easy to lose track of, but that's basically the answer buried in that natural log. And then I plug in 0 here, and I get log of mth minus 0. And then over here, I plug in my limits t final minus 0. Okay? So now I just have to do algebra. I'm most of the way there. So let's take a look at the rest of the solution. What I could do is I could combine these two natural logs. When I subtract two logs, I can make them into one log through division. So notice this term divided by that term. That's what's inside the log. This side, I just got rid of the 0. And then how do I get rid of the log? Well, what I could do is take the exponential function and put this into the exponential function and this into the exponential function, and the equality will be preserved. But what that does is it gets rid of the log, and then we have e to the minus rt on L. Again, I'm solving for I. So I move the mth over, and then I could subtract mth, divide by negative r, and I skipped a couple algebra steps, but that gives you this. Okay, so I just want to also point out before we look at the graph that sometimes, or very often, it's customary to replace L over R with tau, a Greek letter, the same symbol that we used in torque and mechanics. And if you do that, then you could put e to the negative t over tau as long as you define tau as L over R. It's called the time constant. It's an indication of how rapidly the circuit evolves through time. All right, so you may remember this from RC circuits, from mechanics. The 1 minus exponential function to the negative power rises from 0 and slopes up and eventually reaches this mth over r. The way that that works is, remember, this e to the 0 is 1, so the function current starts at 1 minus 1, which is 0. And then, as time goes to infinity, this term goes to 0. So we have 1 minus 1 in the beginning, and then we have 1 minus 0 at the end, which is just going to give us mth over r. The 1 minus exponential function rises from 0 and peaks out at whatever's in front. Another thing I want to point out is that the slope here, the initial slope, m for slope, that's usually what they use in math class for m, the slope, is mth over r. How did I figure that out? I could go back to the differential equation here and see that, oh, mth over L, sorry, that when the current is 0 in the beginning, well, I guess I could do it with this here better. So when the current's 0, I have this. So if I divide by both sides by L, I get mth over L for the di dt, the initial slope. So that's something that comes up also. They'll say, what's the initial rate of change of current? And it would be mth over L. You could see that from the differential equation by realizing in the beginning the current is 0. So that's basically all that's left of the differential equation. All right, so that's increasing current, 4 steps, set up differential equation with Kirchhoff's loop rule, separate the variables, integrate both sides. That's step 2 and 3, and then plug in the limits and solve. Okay? All right, so again, that was for an inductor that had no current in it. You flip the switch down, and then the current builds up like this. The next proof or derivation we're going to do, once the current gets going, and what happens when you try and shut it off? Okay, so decreasing current. Okay, now, before I go in there, pause the video for a minute and see if in your mind you can say the 4 steps to solving a differential equation. Okay, so go ahead and pause and test your memory. Okay, so here they are. If you could not come up with them, you should study these. Okay, comes up throughout physics. Make a differential equation with Kirchhoff's loop rule. Separate the variables. Step 2, get all I on one side, all time on the other. Step 3, integrate both sides. 4, plug in your limits and solve. So let's follow that process with this circuit. So here we have a battery. We flip the switch into A and we let the current build up. So that's like the last problem. It takes time for the current to get to its final value. Eventually the current gets up to its final value and we flip the switch down to B. And then what's left is basically this. Okay, just the resistor and the inductor. And so to find the current as a function of time, I've got to make a differential equation and solve it. So here's step 1, I used the loop rule. Now notice I did a highlighter to show you, here's the loop. Okay, the current's going this way, and this time the M of the inductor will be pushing it forward, keeping it going for a while, and not letting it drop instantaneously to 0, making it gradually drop to 0. So again, the loop rule means we pretend we have a little ant here. He's going to start here and walk around this loop and sum up all the voltages along the way and then get 0 for an answer. So the ant comes to the resistor, walks with the current, right? The current's going in the clockwise direction, so it's coming down like this. So it's going from high voltage to low voltage minus IR, Ohm's law, V equals IR. That's the voltage to the resistor. Encounters the inductor, walks through it. The voltage through an inductor is negative LdI dt. So there, I used Kirchhoff's loop rule. I made a complete loop. My answer for voltage is 0, summing it up. So step 1. Step 2, we got to separate the variables. I got to get all the i's on one side, all the times on the other. So I'm going to move this over here, leaving this. Then what I'm going to do is move the L and the dt to the other side. So I have negative R over L and dt, because the L came over in the bottom and the dt came up in the top. Then I'm going to divide both sides by I, giving me di over I. I integrate from the current I started at, because remember this is decaying, so it starts not at 0 this time. It's starting at some original current and dropping down to some smaller current at some later time. The experiment began at time 0 and ended at time final. The left side just integrates to natural log for our limits, and the dt integrates to t for our limits. We plug in our limits. Log of I minus log of I0, t final and 0 plugged in. Moving on. We could once again combine the 2 logs, right? So make them into 1 log, and then this side I just got rid of the 0. Use the exponential, so the exponential will get rid of that natural log and make this e to the negative, and then multiply the I0 to the other side, and there I go. And a reminder that I could make this negative e to the negative t over tau again, but I left it in terms of the original variables. And this is just a simple exponential decay. That's what this e to the minus function does. Okay, so next thing I want to just point out, something really interesting about inductors is that the inductor can be used to generate a voltage greater than the battery voltage. And I'll show you a dramatic example here. Let's suppose I've got a 6-volt battery. Okay, and I flip the switch into position A, and it's only working against a 2 ohm resistor and an inductor, so it's going in a loop like this. The current after a long time will build up to, from Ohm's law, 6 volts over 2 ohms. I equals V over R, 3 amps. Okay, when I flip the switch to position B, then what happens again is the battery's isolated out of the circuit. So the circuit now is only the 2 ohm resistor and the inductor. But look what I did. I added another resistor here compared to the previous over here. This was just a wire. But look, what I did is I put not just any old resistor, a huge resistor. This is 2 million ohms. 2 mega is 2 million ohms. This was only 2 ohms. So the inductor, remember, it does not let the current drop to 0 instantaneously. It makes it keep going for a while. So that means when I flip the switch to position B, this current cannot drop instantaneously. So even though the battery's gone, there's going to be still 3 amps forced through that. That inductor is going to keep forcing 3 amps. But now not through 2 ohms, through 2 million ohms, because it's got to go in this loop. So I could find the voltage in the inductor at the moment that switch flips down by using Ohm's law, IR. But the resistance now is 2 million plus 2, or 2 million 2 ohms. Actually, I don't even need that 2, it's insignificant. If I multiply these out, I get 6 million volts out of the inductor. The battery was 6 volts. I flip the switch down, and for a split second, I get 6 million volts instead of the 6 volts of the battery. So that's one of the powerful things of inductors. They can be used to generate enormous voltages by slipping in suddenly more resistance into the circuit. This is the basic physics behind automobile spark plugs. You got a 12 volt battery. Spark plug has a gap in your engine. 12 volts is not enough to make a spark like a Van de Graaff generator. But you've got a coil, and when you flip the coil to the spark plug gap is like a high resistance, and then the induction of the coil makes a very large voltage, and a spark occurs, igniting your gasoline. So, very significant, important application of inductance. All right, well, if this is driving the current without the battery there, for a moment it's going to be heating these resistors. That means the inductor was giving these energy, which means there's energy in the inductor by the law of conservation of energy. The magnitude of the energy in an inductor is given by this formula, 1/2 inductance current squared. When we studied this, I used the formula for kinetic energy as a sort of building block or a mnemonic device to help you remember this formula. 1/2 mv squared, so this is like V, the current, and this is like the mass, right? And we talked about that earlier. Inductance is like an inertia. So it's kind of like 1/2 mv squared. All right, so again, I've highlighted these steps. Make sure you can generate these. The rest are details. If you can get here, you're going to be able to get here. It's just algebra. So again, these are the signposts, the important steps of solving these differential equations. All right, let's continue on. All right, so just like with capacitors, you can put inductors into more complicated circuits. These were just simple, like a series circuit kind of example. But here, notice, we've got these two things in parallel, and those are in series with R1. So that's my circuit. I've got a battery, a power supply here, a switch, resistor 1, a break. We can go through the inductor this way or through another resistor this way and complete our circuit. The main concept here is that when the switch flips down, the inductor does not allow current to instantaneously increase. The current was 0 before the switch flipped down. When the switch flips down, at that instant, it's still 0, and it'll gradually leave 0. So once the switch flips down, the current here is 0, so the inductor behaves like an infinite resistor in the beginning. R initial is infinity. I put it in quotes because it's not really a resistance, but it acts like a resistor. So you could think of it as an infinite resistance. No current will pass through in the beginning. But after a long time, the inductor will allow current to build up, and then after a long time, the final resistance, in quotes, could be considered 0. So the inductor then becomes like a wire. In the beginning, it's a blockage, in the end it's like a wire. That's what I mean there. So there's the main concept. And then what you do in the AP test is they have you analyze the circuit in the beginning, initially, and they use the word initially. And that means, at time 0. And then they'll say after a long time. And that means the current when time goes to infinity. And remember, as I've said throughout these review videos, infinity is a relative term. This could be like a millionth of a second. And so for our scale, it's very fast. We're talking a long time on the time scale of this circuit. So that's what we do with a circuit like this in the AP curriculum. They don't have you analyze and figure out the current as a function of time as we did with the differential equations we just solved. You just solve in the beginning for the currents and after a long time. And in this particular example, this is what the circuit looks like when we flip the switch down. Again, this is infinite resistance. It's a blockage. So notice it's not, I don't draw it in here because no current can go through here. So to the battery, it's as if this part of the circuit doesn't exist. So the current just goes like this, and the current is from Ohm's law, V over R. That's the R that the current goes through. I want to point out that the inductance voltage is the same as the voltage on resistor 2 because they're in parallel, right? They're in parallel. Things in parallel share the same voltage. So that means that the voltage of the inductor in the beginning, you could find it from Ohm's law IR. And the voltage of an inductor is L di dt. I left off the minus sign because I'm just comparing the magnitude here. So this is equal to IR through resistor 2. IR. And what this allows me to do is find the time rate of change of the current. In the beginning, when the switch flips down, you could figure out how rapidly the current is increasing by dividing both sides by L. So that's as far as it goes for in the beginning, just finding the current in the circuit, assuming the inductor is a blockage. After a long time, the inductor allows current to pass, and so now the current bypasses resistor 2. None of it goes here, it just goes through the inductor. So the current after a long time is just M over R1. Another thing I didn't put is sometimes they might even have you graph this. Oops. And the current would start at, as we saw, M over R1 plus R2 and rise to M over R1. This is the current. So it would rise like this. So you might have to do that. But to just create a graph like that. So inductors and combination circuits. Here's the main concept. Last thing, LC circuits. What I mean is an inductor and a capacitor, no resistance, no battery. So what I've drawn is the state of the circuit in different phases. Let's suppose in the beginning the capacitor is fully charged and there's no current in the inductor. The capacitor will force current through the inductor, and then eventually as the capacitor depletes, it gets to zero charge. But at that moment, there's current in the inductor. And the inductor will not let the current drop instantly to zero. It keeps it going and makes it decay. So what that means is that the positive charge continues, and then this becomes positive, and the top becomes negative, the opposite of what we had in the beginning. And then the current will want to go this way again, so the capacitor drives it through the inductor. At some time when the capacitor is discharged, now the current's going the opposite way. But again, the inductor is like inertia. It keeps the current going, and it recharges the capacitor. Then this, then this, then this, then that, then that, then that. So what we have is basically like an oscillation, like a mass on a spring. The capacitor acts like a spring. This is like mass, so we've got oscillating current and charge. How do we analyze this mathematically? What we do is we realize that we have energy in the capacitor, then no capacitor energy but inductor energy. Then the inductor energy is 0, and we have all capacitor energy. And then we have all inductor energy. So the energy switches between the capacitor and the inductor. We could write that mathematically as 1/2 Q squared over C is the energy in a capacitor, Q max. So that's the energy of the circuit. Later here, the capacitor has no more energy, it's all in the inductor. 1/2 L I max squared. And then somewhere in between, we could have some energy in the capacitor and some in the inductor. So a problem here, what they might have you solve is maybe they tell you the charge in the beginning and they ask for the maximum current in the inductor. So you would be solving between these two variables. Or another possibility is they say a capacitor begins with, say, 10 microcoulombs of charge. What's the current when there's only 5 microcoulombs of charge? And they give you C and L, and then so you solve for I. So you might be told this, and then you're comparing these two here to this or that. So different parts of this formula with energy conservation. We've got oscillation between the charge and current, therefore the energy oscillates. Also, you can write simple harmonic motion equations. Remember, for x, a mass on a spring, we had x equals amplitude cosine of omega t, where omega was 2 pi over the period. In the case of a mass on a spring, I believe omega came out to be radical k over m. Okay? And you figure that out by making a differential equation here, plugging this in and solving for omega, and you would get this. I didn't show you that because as far as I know, that's not part of the curriculum. It might show up. Who knows? But again, we've gone almost 45 minutes today already, so I'm not going to go into making a differential equation here with a loop rule and plugging this in and solving this out. But that's how you would do it. And then if you solve this for t, you get 2 pi, the period of oscillation as the charge is oscillating back and forth, the time for it to go through all these cycles and return back to here is 2 pi square root of inductance times capacitance. You could plot possibly the charge. If it begins like this, it would be a cosine graph. This again is the period by that formula. And then if you take the derivative of this cosine, you get negative sine. And if you took the derivative, you would find that the current here max is Q over square root of LC, negative Q over square root of LC. Okay? So that's a little LC circuits. You get oscillations like a mass on a spring back and forth. This is current going back and forth between the capacitor and the inductor. And we get energy and period. So there's our review video. Again, this is the highlight. The important step that I want you to memorize or to remember here is the energy analysis and also the period of oscillation. So let's take a look at what we studied in this review video. Again, we learned about the concept of inductors. It's any coil of wire. In fact, the circuit itself is a coil of wire. So even a circuit without an inductor has a tiny inductance, but any coil of wire, what it does is it opposes increases in currents and opposes decreases in currents. It's like inertia, trying to keep I either going or keep it at rest or keep it moving. Okay? Now we learned some equations how to calculate inductance, the voltage produced by an inductor. So these are like the main equations here. And then we studied the solenoid example. So this is kind of a classic example. You know, you want to make sure you remember the highlights here. We learned about inductors in LR circuits for increasing current or for decreasing current, right? So we got exponential decay or the 1 minus exponential rising. In both cases, you use the 4 steps of differential equations. Make sure you know those steps in your mind. Can you chant them out? That's what's going to guide you when you're deriving those current as a function of time. And then we learned about inductors in combination circuits, okay, how the inductor behaves in the beginning, how it behaves at the end, and then oscillations, LR circuits. So that is the last topic video with induction in our last unit. The one thing I didn't cover in this video were Maxwell's equations, but remember I already did a video on Maxwell's equations in the last unit, a nice candlelight video. So if you're rusty on Maxwell's equations, you could go back and look at that nicely done video with a nice mood. So that's it for review videos. We have gone through this very difficult curriculum 2 times now, all throughout the year and through this review topic. So you should congratulate yourselves. If we were in class, I would say, everyone, let's give ourselves a round of applause. You did a lot of hard work. You studied very difficult topics, very sophisticated topics with fields and 3 dimensions, integration, calculus. So you deserve a good pat on the back. So I want to congratulate you for getting through the curriculum twice. And I hope that you have great understanding and that everyone in the class gets 5 out of 5s. That will make us all very happy, and then we could celebrate some more. So I would say see you in the next review video, but there aren't any more. So that's it for our review videos. And maybe I'll say, hopefully I'll see you in class. We'll see how the year goes, right? So hopefully we'll see each other again before the year is out. Okay, bye-bye.